Good morning, kids. Today we're going to talk about some more applications of differential equations. So I'm going to get right to it. I have 3 different examples for you. You'll see that on this sheet there are 5 examples, but that would take forever. So I'm going to do 3 of the examples for you. The first example is a company's revenue is earned at a continuous annual rate of 5% of its net worth. Okay, that seems like important information, so I'm going to underline that. At the same time, the company's payroll obligations amount to $200 million a year paid out continuously. So that seems like important information as well. Write and solve a differential equation that governs the net worth of the company, W in W million dollars. Then find the equilibrium level. So the hard part's going to be just to write and solve the equation, and then the equilibrium, of course, is just when we set it equal to 0 and solve for W. So let's go ahead and start by writing the equation. So the rate of the net worth, they tell us, is equal to 5% of its net worth, so 0.05 times its net worth, which let's call it W, we might as well, minus 200 million a year, so minus the rate of 200 million per year. So the rate of the net worth, if you think about that, that is the change in net worth over the change in time. So we call that dW dt is equal to 0.05 W minus 200. Now, these are all rates, right? It's 0.05 W minus 200 million per year. That's also a rate. And dW dt is, of course, a rate. So this is consistent throughout. Now we're just going to solve this, so I'm going to quickly solve it. First thing I will do is factor out this 0.05, or you could either factor it out or you could divide both sides by it, but I'm just going to factor it out. So dW dt is equal to, because we have to separate our variables. The easiest way to separate our variables is factor out the 0.05. So 0.05 W divided by 0.05 gives us W. 200 divided by 0.05 gives us 4,000. So we get 0.05 W minus 4,000. Now we'll separate the variables, so we'll go ahead and divide both sides by this W minus 4,000, and then we'll multiply both sides by dt. When we do that, we get dW over W minus 4,000 is equal to 0.05 dt. Now all we have to do is solve that. It's fairly simple to solve, so we get a natural log of the absolute value of W minus 4,000 is equal to 0.05 t plus c. Of course, now we're going to raise e to the power of both sides, and then we get our arbitrary constant. We bring the plus c, basically it becomes an e to the c, and then the e to the c becomes an a, right? So basically what we end up with now is W minus 4,000 is equal to a e to the 0.05 t. So now to solve this is a little bit tricky. Well, let's solve this for W first. W equals a e to the 0.05 t plus 4,000. So there's our equation. Now we're not given an initial condition. Now when we're not given an initial condition, we're going to name our own initial condition. So let's say that the net worth at time 0, W of 0, is equal to, what better thing to use than W sub 0, right? So we're just naming a constant that represents our initial condition, or our net worth at time 0, because we're not given one. All right, so we're going to put W sub 0 in for that. So when we plug these in, we put 0 in for t, w sub 0 in for w. So we get w sub 0 is equal to a e to the 0.05 times 0 plus 4,000. But then e to the 0.05 times 0 is 1, so that just becomes an a. Subtract 4,000 from both sides, and we've solved for a. W sub 0 minus 4,000 will always equal a. Alright, so now we can plug that in to our solution that we obtained up above, right? So we have this solution, and then we also have what we have found a to be. We'll come down here, plug both of these in, and we get the following for our solution to the differential equation. W equals 4,000 plus w sub 0 minus 4,000. Make sure you put parentheses around that because that represents a, and a is multiplied by e to the 0.05 t. So that's our answer, or our solution to the equation. So now all we have to do is find the equilibrium. So to find the equilibrium, very easy to do that. We just need to take our original equation and set it equal to 0. Not our solution, but our original equation, right? So dw dt, our original equation, so let me write equilibrium here so nobody gets confused. dw dt equals 0.05 w minus 200. So I'm setting that equal to 0. Oops. So I'm trying to figure out in the long run basically what this is going to be equal to, right? So we're setting the slope equal to 0. So 0.05 w is equal to 200. Divide both sides by 0.05 and we get w equals 4,000. Now that's 4,000 million, right? So 4,000 million, if you think about it, is 4 billion. Okay, so W ends up equaling 4 billion. That's your equilibrium solution. Alright, moving on. Let's go to the next problem, finding a differential equation for terminal velocity. I always consult my husband, the former physics teacher, for this so that I don't mess it up. So Newton's second law of motion is F equals ma, and this is your given. Air resistance is proportional to an object's velocity. So the overall force that we have from air resistance is the mass times the acceleration due to gravity. Well, this is the overall force, including air resistance, excuse me, is the mass times the acceleration due to gravity minus, now, proportional to an object's velocity. So proportional to is always k times something, right? And in this case, it's proportional to the velocity, so it's k times v. All right. So F is equal to mg minus kv. That's the overall force, all right, including the force upward and the force downward when you have an object that is falling. And that's what you're looking at when you're looking for terminal velocity. So I take this, and I'm going to set that equal to ma. Now, mass times acceleration. Well, what is acceleration in terms of, we already have mass on the other side, what is acceleration in terms of velocity? Well, it's the derivative of velocity, so dv dt. So you have mg minus kv equals m times dv dt. So this is going to yield for us in a differential equation for terminal velocity. All right, and then we're going to solve that equation. So let's go ahead and do that now. So I'm going to go ahead first and solve this for dv dt. So I'm going to divide both sides by m, and I'm just going to switch sides on this so I have the dv dt on the left. So dv dt is equal to, now when I divide mg by m, I get g, right? When I divide kv by m, I get k over m times v. So I get g minus k over m times v. Remember that g is the acceleration due to gravity, which is 9.81 meters per second squared, right? We could even, we're not going to put that into our problem, but that's what it is, 9.81 meters per second squared. And then K is our constant, right? And M is our mass. So now what we need to do is solve this equation. Well, what did we do in the last problem? First thing we did was we factored out whatever was in front of our variable or being multiplied by our variable so we could separate variables. So I'm going to factor the k over m out, so I get dv dt is equal to negative k over m times, now if I divide negative k over m times v by negative k over m, of course I get v. If I divide g by negative k over m, it's the same as multiplying it by negative m over k. So I get minus mg over k. Okay, that's just algebra. Now we can go ahead and separate our variables. So we get dv over v minus mg over k is equal to negative k over m times dt. So once we have that, we now can go ahead and get a solution to this. Take the natural log of both sides, so I get natural log of v minus mg over k is equal to negative k over m t plus c. Go ahead, raise e to the power of both sides. E to the c becomes an a, and we get v minus mg over k is equal to a e to the negative k over m times t. So now, what is v equal to? We just have to move the mg over k to the other side. We get v equals a e to the negative k over m times t plus mg over k. So we're almost there for the terminal velocity. The next thing we need to do is plug in an initial condition. Well, let's assume that the velocity at the time 0 is equal to 0. That's a fair assumption. So if we plug that in, we get 0 equals 0 equals a e to the negative k over m times 0 plus mg over k. Of course, a times 1 is what we end up with there, so we get a ends up equaling negative mg over k. So we take those two pieces of information, this solution here, this constant here, and we finish up. So we get v equals mg over k, well, negative mg over k e to the negative k over m times t plus mg over k. So that actually ends up being v equals I'm just going to factor out an mg over k, times, and I'm just going to switch these two. Alright, so 1 minus e to the negative kt over m. Now that's the solution to the equation. Now what happens as t approaches infinity here? What would the terminal velocity end up being as you let t approach infinity? Because that's what we're really looking for. And what it turns out to be as t approaches infinity, we get v equals, well, as t approaches infinity, it's e to the negative kt over m. So you have e to a very high negative exponent, which means that approaches 0. So we get v equals mg over k times 1 minus 0, or v equals mg over k. So that is our terminal velocity, where we have the mass, the acceleration due to gravity, and then k is the constant of proportionality. Alright, so let's move on to the last example. Oops, I forgot to circle that solution. Let's see. Oops, there's Mary. Let me see if I can call upon her father. Tom? Okay, I guess I'm going to have to pause because her father's sleeping. Alright, so starting this third problem, this one is really very, very complicated. There's a lot to it. We have a water reservoir. There's so much information just in the beginning of this that I like to write down the information first so that I can organize it and then go from there. So a water reservoir holds 100 million gallons of water and supplies a city with 1 million gallons a day. Well, apparently Daddy's not able to calm Mary down because she's still crying, but hopefully soon. Alright, so first thing I'm going to write down of my givens is that the reservoir, I'm going to use res for reservoir, holds 100 million gallons. And abbreviation is definitely necessary here. And then the next thing we know is it loses 100 million gallons a day. Now that's okay, so we have this, and then oops, wait a minute, and it supplies a city with 1 million gallons a day. So that means that the reservoir empties out 1 million gallons a day. So it loses 1 million gallons per day. So that's a rate, right? And then the reservoir is partly refilled by a spring which provides 0.9 million gallons a day. All right, so of it's a spring, yes, 0.9 million gallons a day, and the rest of the water, 0.1 million gallons a day, comes from the runoff from surrounding land. All right, so it is refilled by 0.9 million gallons per day of pure H2O, spring water, and then 0.1 million gallons comes from runoff. So 0.1 million gallons per day comes from this runoff. And it says the spring is clean, but the runoff contains salt with a concentration of 0.0001 pound per gallon. Alright, so the runoff has a salt concentration, so with salt concentration of 0.0001 pounds per gallon. There was no salt in the reservoir initially, and the water is well mixed. That is, the outflow contains the concentration of salt in the tank at that instant. So let's just say that there was no salt at the start, and we can assume that all of the math will work in this because the salt is well mixed. Alright? What they want us to find now is we find the concentration of salt in the reservoir as a function of time. Okay, so salt is mixed instantly on entering. Find Q and C, which is the concentration in pounds per gallon. Okay, so first thing we want to do is figure out how C relates to Q. Well, the reservoir holds 100 million gallons. C, the concentration, is going to be equal to Q divided by 100 million pounds per gallon. The rate at which the salt goes into this particular container would be equal to C times the volume per day. Well, what's C? Well, it's C is equal to 0.0001, the concentration, pounds per gallon, and then the volume per day is equal to 0.1 million gallons per day. So times 0.1 million gallons per day. So that's going to give us the rate at which our salt is entering our reservoir. Sorry. So the rate at which it enters, 0.1 million is 1/10 of a million, right? So you're doing 100,000 times 0.0001, so that ends up being actually 10 pounds per day. because, right, the gallons here cancel, so you end up with pounds per day as your units. All right, so the rate in is 10 pounds per day. Let's look at the rate that the salt leaves now. Hope I have space for this. The rate the salt goes out is equal to C times the volume per day so the rate out is equal to, well, C we said was equal to the quantity divided by 100 million pounds per gallon, right? So Q divided by 100 million pounds per gallon, and then that's going to be multiplied by the volume per day, so 0.1 million gallons per day. Oh, now both kids are up. This is my lesson for doing this on a Sunday, all right? To multiply this together now, we end up with, and you can trust me on the math here, just trust me, you end up with, this is 0.1 million, 100,000 over 100, let's see here, 100 million, so you end up with 100. Doesn't seem right, but I'm pretty sure it's right. All right, so hold on 1 minute, kids. I'm going to pause for a second. All right, so I've straightened out my, I thought I saw something wrong in my math there, so there was something wrong. If I do the 0.1 million divided by the 100 million, my rate out is equal to the quantity, the 0.1 divided by the 100 million gives us over 1,000, and then pounds per day. All right, so that tells us the rate out. Now, first thing we want to do is find the change in the quantity of salt, and then we're going to find the change in the concentration. There are two different things. We'll find the concentration formula after we find the quantity formula. So let's go up to the top. I'm going to say dq dt is equal to the rate that it comes in minus the rate that it goes out. That's the change in the quantity. All right, so dq dt, the change in quantity of salt, is going to be equal to the rate that it comes in, which is 10 pounds per day, minus the rate that it goes out, which is, we just found to be Q over 1,000. So now we have to solve this just like usual. I'm going to slide this over a little bit, give myself a little more space. I might shrink it up a bit too. I'm hoping you already have that stuff down, so I think I'm going to need some space here. So when I do this, I get factoring out, same thing we've been doing over and over again. All right, so I'm going to factor out the 1 over 1,000, which is basic, or negative 1 over 1,000, which is basically negative 0.001, so that I can isolate my Q. So I get dq dt is equal to negative 0.001, all right, times Q, okay, I'm going to switch these, all right, so that the Q part comes first, Q, and then when I take 10 and divide it by negative 0.001, I get negative 10,000. All right, so now I can just separate my variables, dq over q. This is the easy part, right? The hard part is setting all of that up. And these are really difficult problems, so don't beat yourself up. I will be posting the answers online. If you need hints, you can take a peek and give yourself some hints. But try them in earnest first before you give yourself a hint. So let me continue with the problem. This is equal to negative 0.001 times dt, and then natural log of q minus 10,000 is equal to negative 0.001 t plus c. And then if we raise e to the power of both sides, we get e to the natural log of this is equal to e to this. And hi, sweetie. Robbie is here, kids, just so you know. Q minus 10,000 is equal to a e to the negative 0.001 t. I'm really rushing through now. I hope you guys are grasping this. This should be the easy part anyways. Q is then equal to a e to the negative 0.001 t plus 10,000. And then, of course, the quantity at time 0 is 0. Alright, so let me draw a little fence here because I'm kind of running into my other work. So since q of 0 is equal to 0, what we end up with, and the reason we know q of 0 is equal to 0 is up at the beginning it says, right over here, no salt at the start. Right? That's why we can assume q of 0 is equal to 0. So plugging that in, we get 0 is equal to a e to the, when we put a 0 in for t, we get an exponent of 0, plus 10,000. Hi, sweetie. Hi. So then we end up with a equal to negative 10,000. Alright, so we've got that. Oops, that I should have circled in green. And then we have this solution up here, so we will combine those two things. When we combine those two things, we get the following. Q equals, let's see here, 10,000 minus 10,000 e to the negative 0.001. Oops. Hi, sweetie.
What are you reading?
I'm writing some stuff to my students. Can you say hello, class?
Hi.
Hi, there you go. Okay, now you gotta say goodbye and go in the other room, okay? Say bye-bye.
Bye-bye.
All right, good job. So we end up with that, and now if we just pull it out, it'll make it easier to work with. If we pull out the 10,000, we get Q equals 10,000 times 1 minus e to the negative 0.001 t. Now, to get the concentration, all we have to do is use that concentration formula. So the concentration formula that we have from above is C equals Q over 100 million. We have Q, so all we need to do is put that Q in there and we're going to have our concentration. Alright, so C is equal to Q, 10,000, times 1 minus e to the negative 0.001 t divided by 100 million. Okay, now 100 million, remember that's, 100 million. So that looks like this, in case you're wondering where I'm getting all these numbers from. So when I cancel 10,000 with 100 million, when I do that division, I get C equals 0.0001 times e to the negative 0.001t. Oops, I forgot my 1 minus. Hold on. Times 1 minus e to the negative 0.001t pounds per gallon. So that's our solution. That is our concentration of salt in this tank. Now, if you think about that, in the long run, as t approaches infinity, right, what would be the amount of salt in the tank? Well, as t approaches infinity, it's e to a negative 0.0001 times infinity. So that is going to end up being a very high negative exponent. So this portion will approach 0. So in the long run, the concentration of salt in this tank as t approaches infinity, C approaches 0.0001 pounds per gallon. Alright, so just that is it. I'm not going to go over any other problems. Your homework, so I'm not going to go over this one, not going to go over this one. The worksheet is going to be your homework. So there are two things today. I forgot to tell you at the beginning of class, but one is this note sheet. The other is the worksheet. It's the applications and modeling homework. So you're going to take that. The entire worksheet is your homework. There are answers online, so you can check out the answers online, and that should help you. But these are tough problems, so good luck. Have fun with it. Remember, math is fun. Have a great day.